we will go back to filter design, and I will just review with you what we did in last week, and then we'll finish that portion, but we're gonna solve more problems this coming week on this. And the homework that I will give is going to be based on whatever filter information we'll do up until today. So today we're solving a problem at the end, and you're going to see them very simple as long as you understand the design approach. So what we said about filters is that there are multiple methods for solving filters, but the one we are following, because it's easier for us and more in alignment with the things that we covered in this class, and more in alignment with the circuit concepts, is what we call the insertion loss method. This is the insertion loss method. And why do we call it insertion loss method? Because we introduce a parameter which is called the insertion loss, and the definition for this parameter is given here. All right, so what we do is practically a ratio between the input from the source, power, divided by the power that eventually gets into the filter. So let me, in fact, talk a little bit about that to make sure that you understand what that really means. So I will write it here. I will put a new page so I can write on it. Okay, so I think it has moved it, but we don't see it quite yet. So let me, all right, okay, I will write it next to it here, it does not matter. So let us consider that when we look at this filter, and if we were to assume, in fact, what do I need to do to open this page up? Let's see whether I can cut this. No. All right, let me go on a separate page for a moment. Okay, that's better.
I think you can cut it by zooming it out. Zoom out.
Okay, it does not matter. I will resolve. Sometimes, you know, it does things that I'm not quite sure what to do with it. But in any case, thank you for telling me though. At this moment, I will write here. So let's assume that we have a voltage source. And then here we have an internal impedance Z sub S. And let's assume that Z sub S is real for a moment. Okay, so this is R sub S. And here, ideally, all right, if we were to match this, remember we have both the matching for, meaning the input here, impedance, will be identical to Z sub S. In this particular case, why do I match it like that? Because Z sub S is real. When your source impedance is real, like here, we always try for best transfer of power from the source to whatever line, circuit, whatever it is, you try to match them. And this is the most power delivered to your line. All right, that's the best relationship for most power to be delivered from your source to your line, if they are real. And of course, you have a transmission line, you have a characteristic impedance. If this is Z0, well, obviously, having an infinite transmission line of characteristic impedance Z0 will achieve that. Okay, so in this particular case, the maximum, how much is the maximum power that goes into the line? Let's call that P incident. All right, and it's real, obviously. We have a voltage, we have a real impedance as internal impedance here, and we have a line that has a real, of course, characteristic impedance. And how much power goes to your line? Who will tell me? Do we not get the power like this? Do you agree with this? Remembering the input and the incident and reflected waves in a transmission line? Do you agree with what I wrote here, or that presents you with some questions? So let me extend that to see why I wrote it like this. Let's assume that I have a line like that. The line is totally matched to my load, okay? So if my incident voltage here is this, and my incident current is this, do I have any reflection coming back from the line?
No, because it's matched.
Exactly. And therefore, the total voltage on my line is going to be V starting at AA prime, and that's going to be only the incident. Do you agree? That's why I put a plus there, because there is no reflected, all right? And if you have the total current at AA prime, it's going to be only the incident, because there is no reflection from the line. No reflection here. All right?
Dr. Katehi?
Yes.
Are those I of AA or IA prime?
A prime. I'll put it. 1 second. All right? So, yeah, because A and A prime indicate the entry point into the line. It's the beginning of the transmission line.
Okay.
All right?
On the diagram, they're all AA, not A prime.
Where?
Yeah, VAA, it's not VA. And IAA.
Where are they not prime?
There's no prime there.
Here you can, that's what you mean. Okay, thank you.
And also the voltage.
Am I okay now?
Yes.
Okay, all right. Now, so this is the incident in the line, okay? And also, how much is the incident voltage, PI, into the line? The total voltage by the source, okay? So the source, let me write it here. So the source generates power, okay? Power. Where does this power go that is generated by the source? Where is it dissipated? Where does it go, in other words? Could you tell me?
It would be dissipated heat in the resistors. I'm not exactly sure if that's how it goes with the transmission lines.
So half of it is going to be dissipated in the resistor, since, let me write it here, since the voltage is here and has one resistor here, which is the R0, all right, from the source impedance and another resistor here, R0, which is in fact from line, all right? That's what you see. The input impedance to the line here, if I were to write it like this, the input impedance to the line at this point is Z0. Do you see that? Therefore, we have this. So half of the power, if the source generates power, half of it goes here and half of it is dissipated here. Do you agree?
Yes.
Is there any energy anywhere? Or is it only real power? Do we have any energy stored anywhere?
Energy equals the integral of P dt.
Are we going to have any energy stored anywhere? I did not ask for it.
No.
Because all our
No.
elements are real.
Yes.
No, exactly, because to have energy stored, you need two circuit elements. Which ones? Inductor or capacitor? All right, there is no other circuit element. If you don't have an inductor, if you don't have a capacitor, there is no storage. There is no energy. It's only real power that is dissipated in the resistor. Okay, so half of the power from the source goes into the transmission line. Okay, so that's my Pi. In reality, if I call this power from the source, call it P sub S for a moment, is gonna be half of P sub S. Do you agree? But it's the incident to the line. Okay. What happens if the line, the way you see it here, practically, all right, it's like this. This resistor, it's an equivalent resistor. It's not connected there like that. So practically, to help us remember that, I will erase these connections. So you remember this is an equivalent. It's seen like this, but there is no actual resistor that is connected. Okay, so the line, if I were then to remove that piece, and then, of course, the line does not have a reflection here, but if you look at the reflection coefficient here, how much is this reflection coefficient? If I call that gamma sub E, sub I. How much is that?
Zero.
How much? Zero, exactly, it's zero because practically you remember that here we had an equivalent resistor that is R0, so practically is R0 minus this is the RS, minus RS, which is also R0, R0 plus RS, so practically is zero. Okay, so every piece, if you like, out of this half of the power that is generated by the source goes to the line. And because the line is lossless, I have not spoken about losses or anything else. If the line eventually goes into a load somewhere, and if the load is matched to, so this is E0, it's another resistor here, all of your power that goes down the line is going to be dissipated in here, in the resistor, all right? That's what is happening. Now, if, however, there is a reflection in here, let's forget about what happens at the end of the line, but we now have a new situation where our source has an R0, but here the line that is somehow has a load somewhere, and let's assume that this load is ZL, has an input reflection, which is not zero. So practically what that means, we have an equivalent impedance here, and it could be in fact even reactive, all right? So we have an equivalent impedance here, equivalent. I call it Z sub I input or Z input. which is not Z naught, and therefore gamma sub I will be Z in, equivalent impedance into the line, minus Z naught over Z in plus Z naught. Okay? If that is the case, how much is the real power that eventually goes into the line? If up in the beginning of the line, right there when the line connects, there is already a reflection like this, and this reflection may be not just a real number, but maybe a complex number, how much is the power that eventually gets into the line and eventually goes here into your resistor at the end, into your impedance? How much is that? Can somebody tell me?
Is it 1 minus gamma squared?
Exactly. The line eventually, because you remember what we said about in transmission lines again. If you have a transmission line and it's terminated, and then here it's your input port. Let's assume that this line is Z naught, has a length L, and this keeps also Z naught. All right, the reflection coefficient here, since it's terminated, the input impedance here, let me start with that and then I'll go to the reflection. The input impedance here, of course, is not gonna be Z naught in general, so it's gonna be an input impedance. And therefore, the reflection coefficient here, gamma in, will be Z in minus Z naught over Z in plus Z naught, as we saw up there. But then, in terms of power, because reflection is in voltages, this is a voltage reflection coefficient. In terms of power, the reflected power is gonna be magnitude square of the incident power, all right? So if the incident power that goes here is this, then part of the power is gonna go back. So the reflected power that is gonna go back is gonna depend on the reflection coefficient. And the reflected power that is gonna go back is here. Just in red to differentiate from the incident. The incident is green. Okay, do you agree with this statement? If you do not remember, please revisit. I have my notes on transmission lines and everything is there. Look at the, revisit that part. Okay, if your reflected is like that, how much is the incident? Like your colleague said, that the incident in the line, okay, so that what goes down the line, and we call it transmitted power somehow, all right? If you want to call it like that or whatever, goes into the transmission line, then P sub T is going to be 1 minus P, look at this, P reflected. Excuse me, not that one. Let me write it from the beginning, and then I don't want to skip a step. So it's going to be P incident minus P reflected. And this is going to give us 1 minus gamma in magnitude square P incident. Get into the end of this, and then you cannot write anymore. So here, P incident. Okay. Incident. Okay, so having said that, if we go back to our problem that we had with the filters, now you see that the ratio PLR PLR is nothing else but the P incident minus P transmitted. Okay, which is P incident divided by 1 minus magnitude of gamma incident square times P incident. And these two cancel out to give us this. So that is nothing else. It's called the insertion loss ratio. We define it like that. So if your reflection is 0, that is 1. If your reflection is 1, that is infinite. What other entity reminds you that kind of thing? That is 1 when you have perfect match, and then it's infinite when you have
Standing wave
ratio?
The standing wave ratio, exactly. It reminds you of the standing wave ratio. But we don't speak about the standing wave ratio here. I just wanted to tell you it varies between 1 and infinity. Okay, and that's a ratio. It gives us some kind of a measure of how much power goes into your circuit. All right. Now then, what we said is, I want you to look into this, but I did not know. Now it shows, okay, cut this part. Now, I want you to look at these derivations because they are extensive, but I'm not gonna cover them here. It's for you just to see. They are extensive derivations that are in your book. I want you to go through them to see that they are not difficult derivations. It's just, you know, algebra, simple stuff. But what that tells us is something extremely important. It tells us that the this power insertion loss ratio is, in fact, can be written in this form. And that was important for people to develop design methodologies. So we're talking about design, not analysis, all right? Design needs to create something for you. Analysis is when you know how to do it and then you just go and verify the performance. Design is when you have only design specifications, as you will see later, and then you need to find out how you're gonna make that filter. So expression here you now these people were able to find 2 separate types of filters. One, they called it maximally flat, because now you can see when you plot your power, your insertion loss ratio, and you plot this as a function. Let me see how LR practically. So I have also to tell you as a, if you see me reversing letters and stuff, since I was very young, I have some form of dyslexia that I'm managing most of the time, but sometimes I don't see when I reverse letters. I just don't see it. I see it later. Okay, so here it's L, R. Okay, just to be. So when you take and here I have reversed it. Okay. When you take that insertion loss ratio and you plot it, then you see that it starts at 1. This is 1 here, 1. It starts at 1, and then it goes to infinity as a function of frequency, obviously. but it's called maximally flat because that region here is like flat. It goes 1, and then it starts growing, but it goes all monotonic. And then if you change the formula for your PLR, which is like here, and then you introduce what we call the Chebyshev polynomial. Don't need to know much about the Chebyshev polynomial per se, but you just need to know that by in making that change right there in the second term of your insertion loss ratio, practically you are able now to create that ripple here. Why is this ripple important? And what we said last time, the ripple is important because by introducing the ripple, especially in this polynomial, you can improve the rejection. Now, I call it rejection, and you say, what kind of rejection is that? Since, you know, it goes high. It goes high because we have expressed it like this, the ratio. It's 1/1 minus magnitude of gamma squared. However, to be able now to explain it a little further, I need to add this page, and now I will, there, that's what your colleague suggested is working. So here practically is the following. P, the insertion loss ratio is practically 1/1 minus gamma sub I squared. And if I were to take a 2-port network, and let's assume that this is my filter, all right? Now, let's assume that I have matched my load and I have matched my input accordingly. So whatever power goes in here, after whatever reflections I may have at the front, all right? I may have, if this is connected to another, to a source that has an internal impedance, and I have not matched in any ways the source with my 2-port network, which is my filter, in that case, there is going to be reflection here, so there is a P incident that goes inside the filter. And if now my filter does not have losses, so practically everything can be, after the initial reflection, delivered to the load, all right, after the initial reflection. So let me call that the transition power or the transfer power. And then if everything, then all of this transfer power is delivered to the load, then practically I have that my power that is delivered to the load, so load here, let me write load so you differentiate. The P load over P transferred, which is, it's identical, all right, is 1, because I said there are no losses inside the filter. And then how much is P transferred is going to be, from here, we have that P load is nothing else but 1 minus this, all right? And that times the incident from the source. Let's call it P incident or P source. Let's call it P incident since we have used that for now. Okay, so your P load, if I look only at power at this point, your P load over your P incident from the source is 1 minus gamma sub I squared, which is the inverse of P L R. Okay, that means something to me. because in reality, if all of it, if the power that comes from the source all goes into the filter and then all goes into the load, because the filter does not have resistive elements, and it's ideal, obviously, whatever, let's assume it performs ideal, that practically all of it goes to the load. So if your gamma sub I is 0, then this is 1. So your load receives the maximum possible power from the source, all right? Your P incident, and in fact, maximum receives at that point, because that's what you get from your source. And if you don't have reflections there in the magnitude of I max of gamma sub I is 0, then practically you have the maximum from the source goes to the load. That's the ideal situation. Never happens like that, obviously.
So,
yes.
So would this only happen when the load impedance the same as the source impedance?
Yes, and it will only happen when practically both are real. Okay, if your source impedance is RS, is Z naught, and your load, at least, I mean, your input impedance here rather than the load, all right? And your Z in here, because your ZL could be different, but your Z in here is equal to RS, all right? And in fact, let me just do it in, when this happens, then your gamma in, which we call gamma sub I here, and to be consistent with the rest of the definition in the book, this is gonna be 0. Do you agree? So this is only happen, it only happens in this particular situation. When whatever comes from your left, whether it's a source in another transmission line, all right, we call that source. If it's another transmission line of characteristic impedance Z naught, and everything is like perfect on that side, then practically the equivalent is to having a source with an internal impedance that is Z naught. And if your input impedance here is the same with this, and they are Z naught, then you get the maximum power. And if that maximum, as this maximum power goes into the filter, if the filter does not have losses, does not have resistors, for example, it's an ideal filter, then everything goes to the load. And in that case, the P load over PI is 1. Okay? In any other, under any other conditions, the P load over PI is not gonna be 1. However, now since we talk about that, what would happen if your source were to have a complex load? What would happen if, and since we are using some hypotheticals here, what would happen if here, I will go back here and say, you know what? I have done the following. I have been able to match my load and get the best filter design. All right, this is my initial load. My real load is here, and the filter is in between. So that my Z input here is the complex conjugate of ZS or ZS or Z input complex conjugate is ZS. Does not matter how I'm gonna write it, but I can write it like that. In that case, I did conjugate matching. What happens when I do conjugate matching? Is the reflection coefficient 0 at this point?
No,
Well,
it'll be
no.
more than
Not
0.
gonna be 0. However, what happens, so I give up in terms of making the reflection coefficient 0, but what happens with conjugate matching, and why is it so popular?
The transmitted power is entirely real because the imaginary parts of the impedance cancel out.
And not only that, but is the maximum in that particular case you can get from the source. So even if for conjugate matching, your gamma in is not 0, you get the best possible or the maximum possible amount of real power that goes inside your filter. And that's the most important thing, all right? Because who cares about whether the reflection is 0 or not? What I care about in circuits is whether I get the maximum of the power that I have generated somewhere. Do you understand that? Because power is very expensive. If you have a cell phone like this, and I have one small battery, I would like to get the maximum I can get out of this battery so it lasts for a long time. But because if every time I scatter my power left and right, you know, without thinking about it, that this battery will last an hour as opposed to lasting 24 hours. And it's a big difference between an hour and 24. So what happens in this particular case is that I say, okay, what are the conditions for highest possible power transfer? Conjugate matching, and that's what I will do. Who cares about perfect match and 0 reflection coefficient if the power that I get is not the maximum that I could? See how I'm thinking? This is how we are thinking about that. But in any case, when however, Z sub S, when Z sub S happens to be real, then I can accomplish both things. Then I can have both gamma in input 0 and maximum power. Delivered. Did you get that?
You mean the gamma input equals to 0 plus that thing, or like both and, like both the gamma equals to 0 and maximum power delivered?
Plus, what did I say plus? Plus means both happen at the same time. Okay. Now, so now I spoke about what goes inside your filter. So practically, that was important to remind you, right? So going back to our filter. So the power that goes into the load. This is important to me because I want to deliver things, all right? If you're a receiver and you put a filter, you don't want to lose power in your filter. You want from your antenna, which is your source, to go directly and have the maximum power to go into your filter. So conjugate matching is always very important, unless you have an antenna that provides you with a real input impedance, all right? And then, so after that, I'm looking at developing a filter that sends the maximum power down to the load. So that's my important parameter. And then I find that this is 1 minus P incident, okay, from the source. All right, that is important. That's what we understand. If you plot this one, and especially if you do it in, take the ratio, P load over P incident, okay? And then you take 10 logarithms since they are powers. Then in that case, what you're gonna see here will reverse themselves and they will look like this. Let me make those a lot smaller now. There. So practically I'm gonna have the following. If I plot this number in dBs, I will have 0 dBs here for 1 when it happens and I have maximum, all right? Whenever that happens, I will have, let's assume that we'll have a low pass filter. It's gonna be 0 here in dBs, and then from here it's gonna go down, all right? If I were to do the same filter This is the maximally flat, the way I've written it, because it says it's totally flat there. But if I were to use a Chebyshev design, then it would look like this. See, what I gain from Chebyshev is what I see here, which I call rejection. Why do I call rejection? Because ideally in a low pass filter, you remember how we showed the low pass filters before with simplicity? We want the low frequencies to go in, and we would like to be really clean as we cut the high frequencies. Ideally, if I could, I will have a low pass filter that looks like that. Like a pulse. It sends everything through at low frequencies, and at some point I cut everything and nothing goes through. Well, it does not happen really like this. So the fastest you can reject in the rejection region, the better off you're going to be as a filter. And that's why the Chebyshev, it's a good one. It's a good design because it gives you this. Okay, now with that, I would like to go and talk about the low pass prototype. And I gave you some, I'm practically reviewing some things here. So we talked about that. The design processes, filter specs, you design a low pass prototype, and then you do two very important for a low pass transformations, a frequency transformation and an impedance transformation. Why is that? Because when you start with a prototype, the prototype tends to be like, it's not a real filter. It's like a design toy. It's like a tool, all right, we're using. It doesn't mean anything because the prototype has as you said, most of you, a cutoff frequency of 1 without units means nothing. It has a source, is excited by a source that has an internal impedance of 1 with no units. What does that mean? Nothing. And is connected to a load that is also 1. Nothing. Okay? So practically, it's not a filter. It's like something we've made up in the process. And so the transformations will take that little gimmick that we put together and then we'll make it into a filter. So now I start with the design. These are the specs that I have in this box. It says, I need a low pass filter. That's one specification. I need a cutoff frequency of 10 gigahertz. So at some point, however I define that cutoff frequency, I need from that point on to see good rejection. That's what it says. From that cutoff frequency, I need to start seeing good rejection. And then it then gives the termination. I would like to have I would like it to be terminated at a load of RL. I would like to have a source impedance of 50 ohms or not. And I would like it to have a rejection of 20 dBs at 3 times the cutoff frequency. That's how I designed this one. I changed some things from last time, but this is the one that you have in your notes. And then after I design this, first I have to design and then I have to look at its properties. So, and what I said is that we go to graphs. Those graphs exist in the book and I have copied them here. And they're graphs that they were taken out of what we call a handbook on filter design. In fact, it's a book like this. As you can see it, for some time, this book was considered to be, if you look at it, it's like all of it has been typed on a typewriter of the time. It's an old book that was done before the war. And it's like, people have it as a Bible. Those filter designers would have that. Now, of course, you don't need that. It's only for historic purposes that we keep it. But these graphs were first initially designed by a group of scientists before the war, and then kept before then. So what do? First of all, you say, okay, I'm going to start with my prototype. Let's look at the rejection. The rejection is very important because that tells you how many sections you are going to have in your prototype. Every section in the prototype is one resonating element. every section is like an inductor or a capacitor, resonating only. You cannot have sections which are resistors with only the last one, which is your load. And it's not really a section, all right? It's just the last one, we call it n+1. So if, for example, you say my filter has n sections, capital N, that means that I have n resonating elements. So I have a combination of inductors and capacitors. Okay, so I don't know that yet, however. So I go here and say, okay, I want to have a cutoff. Let me see what time it is. Okay, a couple of more minutes and we'll continue next time. I would like to have a 20 dB rejection at 3 times my cutoff frequency, omega sub c. So I have to go at the frequency omega, which is 3 times omega sub c. So practically that is going to give me equal to 2, because here you see the horizontal axis shows the magnitude of omega over omega sub c minus 1. So it's going to be 3 minus 1 is 2. So I have to go to number 2, draw a line perpendicular vertical, and then draw a horizontal from 20 and find what section goes the closest to that point. And since I don't try to go to many sections for no good reason, and because I'm very close to 20 dBs with something very close to 2, I say I'm going to select n equals 2. Okay. There are now some specifications you need to keep in mind, because as I said, you have the ability that you have is to go over, and let me now also after this.
Professor?
Yes.
Where did you get omega is 3 times omega sub c?
I said it's 3 times the cutoff frequency. I need a rejection, see, up there. Okay, so now, and this is the last one I'm gonna do. I just wanna tell you that your prototype, did I say something? I said add. Okay, here it is. What did I say? Your prototype is gonna look like a sequence of stages, all right? We call them sections, stages, something like that. So it's gonna look like either something like this. You can either start with an inductance, and then always the series elements will be inductances for the prototype. The prototype is always low pass, always, 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 the prototype. So all of your inductances are in series, all of your capacitances are in shunt. Now and then, how do you count? This is G1, G2, G3, G4, G5, G6 for this one. Mine said G is n equals to 2, all right? I found from my rejection. That's what specifies the number of sections. The rejection specifies the number of sections. So how many I will have? Only 2. That means that mine is gonna have only this and this. Simple LC. And practically also it says that this is my G1, this is my G2, and this is gonna be the source resistance, which is called G0 and is 1. And this is gonna be my load for prototype is called G2 plus 1, to remind you that that's not part of the filter. And that's a resistor and it's 1. It depends what is conductance or resistance, but it's 1. So this part here is your input. So practically I can have a source here. This is your output and this is your filter. And in fact, your filter is right this one. So practically I can go, oh, okay. Your filter is only the red one. The purple is your source and then the load. And then from there, now that I reviewed the whole thing, I will practically what we are going to do next time is go and realize it. We'll read the values, and you read the values. You don't calculate them yourselves. You will read them out of tables, and then we'll apply the two transformations to be able to make a filter out of it. And next time, in fact, we are going to do a number of examples. We'll do both low pass, and in fact, we'll focus on low pass, but both in maximally flat and also Chebyshev. And then Wednesday, we are going to do band pass filters because we need to introduce some other transformations to go from a low pass to band pass or high pass or whatever else other than the low pass. We need to include some additional transformations. Any questions so far? So your homework is going to have to design practically to go through these steps for designing some low pass filters. And by Monday morning, we will also have, and you will see them here also, the frequency and impedance transformations, just multiply by a coefficient to find the filter. So if you read this, and I will do some examples also today, if you read this, you will find it's going to be a very easy exercise at this point. When it gets a little more complex is when you go to other pass bands and you do some other things to make the filters more specific. Any questions?
I've heard like somehow before you said there might be some makeup assignments near midterm and final. Will there be?
Yes, there is, of course. And it will probably be a makeup assignment next Sunday.
Okay.
Okay, any other questions? I will announce that on Monday, rather. Okay, thank you so much. And those of you who wanna, quiz, I'm gonna turn it on right now and you're gonna have, okay, for the quiz, I had somebody who suggested that I keep it open until the next time we have lecture. Next lecture is going to be on Monday. I don't want to keep that quiz so far open, so I would keep it open until Sunday night. Excuse me, Saturday night. So you have tomorrow, this evening, and tomorrow to be able to do that. Okay, I'm not going to keep it until, I mean, it does not make sense to keep it open until then. It's just a quiz on conjugate matching, as a matter of fact. So I'm gonna turn it on right now. And make sure that I turn it on. Okay, what happened? There you go. There. And Tawhat. Okay, this one, the majority you did very well. Correct only responses, all of the, you had to apply to have only the correct responses, only 32 out of 55 had all of the correct responses. So we'll talk about this on Monday. Let me now go to this one and I assign the quiz. So I assigned it. Okay, you should be able to then access it. All right, I'll talk to you later in about less than half an hour for office hours. Thank you.
Have a nice weekend.
Thank you, you too.
See you, Professor.